Hi guys, today we're going to learn about Euler's number. We'll start off by recalling something that we looked at last year was the compound interest formula. A equals P times 1 plus R over K to the exponent KT. Okay, we saw it a little bit differently last year. It looked like this. 1 plus I to the exponent N, where I was equal to the interest rate per compounding period. And the way that we got that is we took the interest rate per year, which is R, and we divided it by the number of compounding periods, which was K. And same thing with the N. N was the number of compounding periods, which is the number of compounding periods per year. K times the number of years, T. Okay, so now we're going to manipulate the formula a little bit. So we're going to say let N equal K over R. Okay, not R over K, K over R. So now we're going to make a couple of manipulations here. So the first one is R times N is equal to K. We just multiply it up. That's the first one. And now the second one is we're going to take the reciprocal of both sides. We're going to have that 1 over N is equal to R over K. Okay, and now we're going to substitute into our formula again, and it's going to look like this. A is equal to P, 1 plus 1 over N to the exponent R N T. All right, so now Euler's number actually came about as he was trying to solve a problem from another famous mathematician named Bernoulli. And Bernoulli's problem was if I had a certain amount of money and it compounded indefinitely, how much would that equal after a certain time period? Okay, so we're going to go through this problem. So it says, now suppose that we invest $1 for 1 year at an interest rate of 100% per year. Let's figure out what the $1 will grow to under each compounding period. Okay, so what we have here is we have our P is equal to $1. We have our R is equal to 100%, so as its decimal equivalent, that's just 1. And our time period T is also equal to 1. So if we compound annually, we're going to get that A is equal to $1. I'm not going to write this anymore, just for this one here. 1 plus 1 over N, which is 1, to the exponent. Now, if we look at the formula, the R is 1, the T is 1, so it's just to the exponent N. So that's going to be equal to 1. Okay, and no problem here. We're going to have 1 times 2, which is $2, which is what we would expect, right? Okay, now let's look at semi-annually. So we're going to say that A is equal to, I'm not going to write the dollar up front, it's just going to be 1 plus 1 over 2 to the 2. So if we compound semi-annually, that $1 investment is now going to be worth $2.25. Okay, let's go monthly. So A is equal to 1 plus 1 over 12 to the exponent 12. And this is equal to $2.61. I'll just write it 3 decimal places there. Okay, it's getting bigger. Now, the question is this number going to continue to get bigger and bigger and bigger and bigger? Well, let's see. Let's look at daily now. So daily, we're going to get 1 plus 1 over 365 to the exponent 365. And this is equal to, what? Give me a minute here. This is equal to 2.71. I gotta write them all down. 4, 5, 6, 7, 4, 8, 2. Okay, now I said, okay, infinitely. Well, for infinitely, let's just take a large number. Let's say 1,000,000. So let's go. So this is going to compound 1,000,000 times in a year. and this is equal to 2.71828 ... keeps going. Now if we notice, daily is 2.71, and if $2.71, if I go a million times, it's also $2, and it's actually $2.72 to round it, but it's pretty close, right? So as you see there, it grows quickly and then it levels right off. And this number here is actually the number called Euler's number. So Euler's number is defined as the limit as n goes to infinity, 1 plus 1 over n to the n, and it is equal to 2.718281828 ... It is irrational. It goes on forever. All right, so this number here is a hugely important number in mathematics, as you'll see as we move through this unit. Okay, so recall that the inverse of an exponential function is a logarithmic function. So what we learned about advanced functions is the base power 10 function. So instead of y equals 10 to the x, then the inverse is y equals log base 10x, but we just write y equals log x without the 10 because that's the default. So if we have y equals e to the x, okay, remember what e is the number, right? 2.7182, etc., etc. Then the inverse is y equals log base ex, right? But since Euler's number is so important, it is given a special designation as the natural logarithm. And we simply write, instead of writing y equals log ex, we just write y equals ln x, and that's ln. That's how you say that, ln x, okay? And this button exists on your calculator. Okay, so on my calculator, it is above the 2 key. All right, so here are the properties. So ln e, okay, remember what that is. That's the same thing as saying log e, okay, and that's just equal to 1. Okay, we don't ever write log e though, we just write like that. Okay, ln e to the x. Okay, if we use our rules, that is x times ln e, which is simply equal to x times 1, which is x. And e to the ln x is equal to simply the exponent part, which is x of the ln. Okay, and I'll just show you why here, because it's probably not that intuitive. So suppose we say e to the ln x is equal to some number y. Now let's take the ln of both sides. Okay, and we'll use our logarithmic rules, and we write the ln x out front. So I'll just come over here. Ln x times ln e equals ln y. Remember, ln e is 1, so we get ln x is equal to ln y, and that means that x is equal to y. So just like we said here, x is equal to y. Okay, perfect. So now we're going to simplify a couple of examples here. So the first one is ln e to the 4x, and we're going to use our rule 2, and this is just equal to 4x times ln e, which is simply 4x. Okay, part B, we're going to use our rule 3, and that's simply equal to 4x. And the last one, we're going to bring this up front. So this is 2x ln e minus x ln e, which is just 2x minus x, which equals x. Perfect. Okay, now our last set of examples, just have an exponential equation, base e, and we're going to solve. So what we did last year when we had this is we took the log of both sides, okay, but because we're dealing with e here, we're going to take the ln of both sides and get the same result. So we have ln e to the 3x is equal to ln 10. Bring the 3x out front, or just write 3x equals ln 10, and then x is equal to ln 10 divided by 3, and x is equal to 0.77 approximately. Okay, next one here, here's our rule. So we have that this simply 2x is equal to 4.9, which means x is equal to 4.9 divided by 2, which means x is equal to 2.45. Good. And now the last one, we don't have a base e here, so it doesn't matter. We can do the log of both sides or the ln of both sides. They both work. So let's do the ln. So we have ln 3 to the x is equal to ln 20. Bring the x out front. X times ln 3 equals ln 20. And x is equal to ln 20 divided by ln 3, which is 2.73. And that's it for today. And there's your sign work. Enjoy.